Okay, so let's get started. I hope everyone's having a good day. What we were working on, well, okay, sorry. First reminder, homework Friday, and then formal reports are coming at the end of term. What we've been working on is developing a new fitting method, and in a lot of ways, it's very similar to what we did for the linear fits. We just have extra fit parameters that are these coefficients of all these functions of x. And the only restriction was that whatever these functions of x are, they can't involve the unknown parameters that we're trying to determine. So they can't involve any of the a coefficients. Okay, so the idea as always is we imagine that we've measured a set of data x and y plus or minus sigma, and maybe there's n of those data points. And what we're trying to do is determine, based on those measurements, what are the best values for all the a coefficients, as well as their uncertainties. What we ended up doing is writing this in terms of a matrix equation. So we had that beta was equal to alpha times a. We wanted to isolate that a column matrix. And so what this epsilon represents is a square matrix that's the inverse of the alpha matrix. And so we had a way of, this was convenient because we know everything that we need to calculate the elements of beta, which is a column matrix. And so beta, the elements look like this, where it's going to be a column. So there's going to be the top entry in the column would be the L equals 1, then we'd have L equals 2, all the way down to L equals m. Okay, and then the A column matrix was just the A coefficients, A1, A2, A3, down to AM. And then alpha was a square matrix, and so it has two indices, the row and the column indice. Alpha is symmetric, so it doesn't matter if you switch the order of K and L. And it was determined by the product of these two functions of f divided by sigma squared. One thing that's important to note, especially for what we're going to do today, is that the only place where y appears is in the beta matrix. So this alpha is completely independent of y. So alpha is independent of the yi values. Because epsilon is going to be just the inverse of alpha, it will also be independent of y. And so we'll say, since epsilon is equal to alpha inverse, it is also independent of y. We'll put yi, I guess. Okay, so what we want to do today is show that the diagonal elements of the epsilon matrix, which is called the error matrix or the covariance matrix or the inverse of alpha, those diagonal elements will give the uncertainties in our best fit parameters. Okay, and so that's the goal for today. So what we're going to do is we're going to apply the usual method of propagation of errors to AL. So AL is just going to be one of our coefficients that we've determined from this best fit, and it's going to be a function of all of the different measurements of the y values. And so we're going to have to take partial derivatives of this AL with respect to y. Okay, so the uncertainty in the AL parameter squared is going to be given by, well, it's going to be the derivative of AL with respect to y1 times sigma 1 squared plus the derivative with respect to y2 times sigma 2 squared. And it will keep going up to the nth, the nth measurement. So it's going to be the derivative of AL with respect to yn times sigma n squared. And so we could summarize all of this, writing it as a sum. I'll write it as j equals 1 to n of the derivative of AL with respect to yj times, this is j times sigma j, and all of that squared. Okay, so in order to actually do these partial derivatives, we have to write down an expression for the AL in terms of all of these variables, the measurements of the y values. So let's do this by an example. So if m was equal to 3, let's imagine, I think last time we did all of our examples, imagine we're going to do a fit to a quadratic. So it was like a1 plus a2x plus a3x squared. So if you'd like, you could have that picture in your mind for an m equals 3. So if m equals 3, then we would have 3 fit parameters expressed in terms of 3 by 3 square matrix, and the square matrix elements are epsilon 1, 1, epsilon 1, 2, epsilon 1, 3. It's symmetric, so whether you write 2, 1 or 1, 2 in these positions doesn't matter. And then 2, 2. This would be 2, 3. This would be epsilon 1, 3, 2, 3, and then 3, 3. And then we would have our elements of the beta matrix. And the beta matrix is where the y dependence will come in. So the beta elements depend on yi. Okay, so let's just write out some of the expressions that we would get. So for, let's say the L equals 1, right? We're going to find A1. We just have to do this matrix multiplication, and we would express A1 would be equal to, let's see, epsilon 1, 1 times beta 1 plus epsilon 1, 2 times beta 2 times epsilon 1, 3 times beta 3. So did I keep saying times? It's plus epsilon 1, 3 times beta 3. All right, and so we could do this for all of them. We would just change the first indice on the epsilon to 2 for L equals 2 and 3 for L equals 3. All right, well, in general, we can express, let's see, AL is going to be the sum of k equals 1 to m epsilon KL times beta K. And let's just imagine that we were to expand this out. So if we actually do the sum for n equals 3, just 1 sec, we would get 1 times 1 plus 2 times 2 plus 3 times 3, and so 2 times 2 and 3 times 3. So that all works. And then if we put, say, L equals 1, we'd get 1 for all of our epsilon coefficients. So there's a 1 here, a 1 here, a 1 here. So that certainly works for this example, and it would work for all the others as well. Yeah.
It'll make a difference if it's symmetric of your indices in the matrix. Shouldn't it be like 1, 1, 1, 2, 1, 3,
Yeah, that's right. So I intentionally put these as the same in the same order just to emphasize that it's symmetric. But yeah, you're right. In general, if you had a matrix that wasn't symmetric, you wouldn't want to write it that way. Yeah. Yeah. So this is symmetric. Okay, good. Now, what we're going to do is we need to take partial derivatives with respect to y to find the uncertainty, and the y dependence is all in the beta. And so I'm just going to write out what the beta k is, and all we're going to do is we're going to use this form. I just change this to a k in the C. Okay. All right. So subbing in our expression for beta k is going to give, so let's see, AL is going to be the sum of k equals 1 to m epsilon KL. So that's all exactly the same. And now what's inside here, inside these brackets, is going to be our beta k. So it's the sum of I equals 1 to n 1 over sigma I squared. There is a yi times fk xi. Okay, and so there's the y dependence. All right. So now we're in a position to actually evaluate this derivative. So the epsilon, we already said, was independent of y, so we can move our derivative inside. And so let's see, this is going to be the sum of k equals 1 to m epsilon KL. And I'll keep my bracket here. I equals 1 to n 1 over sigma I squared. So far, all of these things have no y dependence, so our derivative just moves past all of it and then hits this yi. And so this is going to be dyi, dyj, and then we have fk of xi. All right, and we've done this a bunch of times. You already know that this is the Kronecker delta function, the killer of sums, okay? And so what this is going to do is it's going to kill the sum over I, and it's going to force all of the I indices to be equal to j. And of course, when I is equal to j in this delta, we have delta jj, which is just a 1. And so this just becomes a 1. Okay, so what we end up with then is the sum of k equals 1 to m epsilon KL. And then let's see, we're going to get fk of xj now, divided by sigma j squared. Okay, and that's it, sigma j squared. Okay, good. Now, what we have to end up doing in the end is to find the uncertainty in, say, AL, so we want to find sigma L, is we're going to have to end up squaring these partial derivatives, right? So it's partial derivatives squared here. So what we're going to do is we're going to define a quantity that involves the product of these two partial of this partial derivative. Okay, so to find the uncertainties in say AL, we will need to know stuff like, whoops. We will need to know things like DAL, DYJ squared. Okay, so let's define the following quantity. It's going to be sigma AL prime squared. And it's going to involve the product of this partial derivative. This should be a subscript. That doesn't look good. So this is a little subscript. So it'll involve the product of this partial derivative with the partial derivative of AL prime with respect to, say, Y and some other subscript. So what's going to be the sum of J equals 1 to N of sigma J squared, and then it's going to be DAL DYJ, and then it's going to be DAL prime, oh, sorry, DYJ. So that's the thing I wanted to find. And then what we'll do is, if we set L equal to L prime in the end, then we have sigma squared times the square of this partial derivative. And that's what's inside our propagation of errors. So with this definition, the uncertainty in AL is found by setting L equal to L prime, right? And so then in that case, we would get sigma AL squared is going to be defined to be the sigma AL squared, which will just end up being the sum of J equals 1 to N of sigma J squared DAL DYJ squared. Okay, the reason that we're going to define this quantity in this way is because we're going to find that actually this is going to give all the elements of that epsilon matrix. When L and L prime are equal, those will be the diagonal elements. So we would have the 1, 1, the 2, 2, the 3, 3 elements. When L and L prime are not equal, they'll end up being the entries, the off diagonal entries of the epsilon matrix. Okay. All right. So we have sigma AL prime squared is going to be equal to. So all we're going to do now, and it would be a bit of writing, is we're going to take the result at the top of the page, and the top of the page is this, the DAL DYI derivative. And we're going to take that result at the top and we'll put it in here and here. And so we'll end up with 3 different sums. So we'll have this sum over J, the sum over K, and then a sum over some other variable for the second partial derivative. All right, so it'll be a bit of writing, but that's okay. This is going to be J equals 1 to N. Okay, and then we get sigma J squared. And so we've written down this part. Now we put in the first of our 2 derivatives. Okay, so we'll put it in a bracket here. It'll be the sum of K equals 1 to M epsilon KL FK XJ over sigma J squared. And so I just wrote down that expression at the top exactly as it is. Okay, so now we're going to have another sum. I'll use an indice P for this case. It's a sum from 1 to M, and then we'll have epsilon P
L prime. Epsilon P L prime. And then we have FP of xj over sigma j squared. This is all going to fit just barely. Okay, so there's our big mess. So it doesn't look good right now, but what we're going to do is we're going to try to clean this up a little bit. The first thing we can do is just say we have sigma j squared and we have 1 over sigma j squared here. We have another 1 over sigma j squared. We can cancel those. I can do that cancellation, like I could take this sigma j over here, because as long as I don't take it outside of a sum, that's over j. So we end up doing this cancellation. And then I'm going to reorder the sums. So I'm going to take this sum and move it out here. As long as nothing has a j subscript, it can come outside the j sum. So we'll grab this thing, and it's going to end up going out here. Okay, and then we have another sum. This is over p. There's no j subscripts here, so all of this will also come outside the j sum.
What about the xj?
The xj, like here?
Yeah.
Yeah, so that one I cannot pull outside the j sum.
So just.
Yeah, just the thing under the, above the blue. So I'm gonna leave the fk of xj inside. All right, and then this green one will come and it'll sit over here. All right, so let's see what it looks like when we make those changes. So we're gonna have sigma al prime squared is equal to. Okay, the sum over k is the first thing we'll write. So we'll have the sum over k. And then I'm going to put a big brace here. And then we have the epsilon kl. So that's all the blue stuff taken out. And then we're going to have the sum over p. And then we'll have a different kind of bracket, epsilon pl prime. Okay, and so that's all the green stuff that comes out. What's left is a sum over j. And we have 1 over sigma squared, this thing. And then we have the products of our two f functions. So we have fk of xj and fp of xj. And then we just have to close all of our brackets. Okay, good. Now, does this remind you of anything? This 1 over sigma squared f times f? Let's go look back over here. 1 over sigma squared f times f. Okay, so that stuff inside the final sum, it's a sum over j from 1 to n, is just this alpha matrix. It's the elements of the alpha matrix. We have an L and what was it, a P? So it would probably be alpha LP, I think. But other than that, it's the same thing. So these are the elements of the alpha matrix, right? So it's alpha K P, I guess. I said L, but I was thinking this was an L, but it's a K, so it's alpha KP. All right. Now let's just think for a second. Let's see if we can anticipate what's going to happen here. We're going to have this thing where we have epsilon times alpha. What's the relationship between alpha and epsilon? They're inverses. And so if you took the product of an alpha matrix and a epsilon matrix, what would you get? The identity, that's right. So that's what we're gonna work towards, and that's gonna simplify this thing a lot, okay? You know, maybe you could even see what's gonna happen if all of this stuff ends up just being the identity. Then we have epsilon times the identity, which is gonna be just the epsilon. And so it's gonna turn out that these epsilon elements give us the square of the uncertainties. That's where we're headed. Okay, so what we have then is sigma AL prime squared is equal to the sum over K equals 1 to M. Epsilon KL times the sum of P equals 1 to M. So then we get epsilon PL prime, and then we get alpha KP. Okay, so let's consider, for example, the 3x3 case of epsilon times alpha. Okay, we'll have a bunch of writing here, but we're going to have epsilon 1, 1, epsilon 1, 2, 1, 3, 1, 2, 2, 2, what's this, 2, 3, 1, 3, 2, 3, and 3, 3, and then we're going to take a product with alpha 1, 3, 1, 2, 2, 2, 2, 3, 1, 3, 2, 3, and 3, 3. And we know that that has to be the identity matrix because this is just alpha inverse. And so that has to be equal to the identity matrix. Okay. What we'll do is we'll expand out some of these. I'm not going to do the whole products, but we'll do like say this one times this, and then we'll do a couple of them. One that's equal to 1 and one that's equal to 0. And then I want to compare it to what we have here in the round brackets. Okay, so let's take the first element. So epsilon 1, 1 times alpha 1, 1. Epsilon 1, 1, alpha 1, 1 plus, I guess, epsilon 1, 2, alpha 1, 2 plus epsilon 1, 3, alpha 1, 3. That has to be just equal to 1, right? It's that first element in the upper left corner. And so we'll take a second element. Just as an example here, let's do that first row times the second column, I think. So we'll get epsilon 1, 1, alpha 1, 2, plus epsilon 1, 2, alpha 2, 2, plus epsilon 1, 3, alpha 2, 3. And that has to be the top row, second column on the right-hand side is a 0 in the identity matrix. This has to be 0. And then, of course, we could just keep going. All right. So I want to compare to the sum that we have. P equals 1 to M of, it's the sum, this epsilon PL prime, alpha KP. So this would be epsilon PL prime, alpha KP. And if we were to write out the sum for, let's just say M equals 3 in this case. So this would be M equals 3 in our example. So we would get epsilon 1 L prime alpha K 1 plus epsilon 2 L prime alpha K2 plus epsilon 3 L prime alpha K3. And so if we want to compare to that first expression on the top, we should set L prime equal to K equal to 1. So let's try L prime equal K equal to 1. And then we would get the epsilon 1, 1, alpha 1, 1 plus epsilon 2, 1, alpha 1, 2 plus epsilon 3, 1, alpha 1, 3. Some of these indices are in different orders, but remember, these are symmetric matrices. And so by that first equation, so let's call this equation A, this has to be equal to 1 by equation A. All right. And so the next thing we could do is we could try, let's see, if we want to compare to the second one, I want epsilon 1, 1 to start. So L prime is 1. So let's try L prime is equal to 1 and K. Let's see, I need a alpha 2, 1 or a 1, 2. So K must be equal to 2. So let's try K equals 2. Okay, and so we would get epsilon 1, 1, alpha 2, 1 plus epsilon 2, 1, alpha 2, 2 plus epsilon 3, 1, alpha 2, 3. And if we call this equation B, I hope this looks like equation B, and it does if we could swap some of those indices. Good, and so this must be 0 by equation B. And you could do this for any of the matrix multiplication examples that we've done. We've just done 2 of them. There's 9 for a 3 by 3 matrix. You could check all 9 of them. They'll all turn out like this. If you have L prime equal to K, that'll be one of the diagonal elements. Those sums will all be equal to 1. When L prime is not equal to K, you're going to be finding one of those off diagonal elements, and they'll all be equal to 0. Okay, so in general, it turns out that the sum that we have is just equal to our good old friend, the Kronecker delta function, which gives the elements of the identity matrix. So this gives the elements of the identity matrix. Okay, so we're getting pretty close to where we want to be. What we're going to do is we're going to sub this result all the way back into this one. So maybe we should call this something. Let's call this equation asterisk. All right, so we're going to get a sum over K of epsilon KL, and then we'll stick our delta function in there. So we're going to sub this result into star. And you know what's going to happen. That delta function is going to kill the sum for us. Okay, so equation star was an equation for the sigma squared of AL prime. And what we had is a sum over P from 1 to M. And then we had epsilon PL prime. And then we had this other sum, which we've just determined is equal to the delta function, delta L prime of K. This sum will require that, let's see, L prime and K be equal to each other.
K, no.
This was sorry, where
Sum was over K.
the sum was over K. Oh, right. Yes, you're right. Thank you. So yeah, what you're saying is that this should be the sum of K, right? Yes. Thank you. It's even a K in my notes. Okay, good. Good. Right, so we're gonna sum over values of K, and the only one that's gonna survive is when L prime is equal to K. All right, or K is equal to L prime is what I should say. Okay, so, and then what am I doing wrong? So I'm making a bunch of mistakes, aren't I?
The other one's case.
Yeah. So this should be an epsilon K now. Not, I wrote down P, but it should be a K. So I wrote down P twice when I wanted to write down K. This makes more sense. Okay, good.
Can you go back to the other one you changed this time?
Sorry, which one?
The one that you had changed the other.
So, okay, let me just copy this thing and let me get this thing right. So what we're working on is this KL, epsilon KL. Epsilon K, this should just be an L, right? There we go. I finally got it. So sorry, now what was your question? No, it was all in here. I was making all my mistakes here. I got this indice wrong, and then I got both of these indices wrong. But I think they're right now, right?
But it was all in the same. Like that.
Yeah, all in this last equation, yeah. So does everyone agree that I've got this right finally? Yes, okay, good, thank you. This makes more sense now because the delta function is going to force K to be equal to L prime. So that is going to become L prime. Good. So this just ends up being L times L prime. And I put the L first, but it doesn't matter. You can switch the order. That's fine. So therefore, sigma AL prime squared is equal to epsilon L prime. So the takeaway is that the elements of the epsilon matrix give the uncertainties in the best fit parameters. And so that's the result that we were anticipating. And like I said last time, it's a very nice result because we need to calculate the epsilon matrix in order to find the best fit parameters in the first place. And lo and behold, that matrix also has all the information that we need for the uncertainty. So we don't have to do any additional calculations to find those uncertainty elements. So let me just summarize everything that we've done. So example, 4, 3 parameters. Our best fit parameters are going to be A1, A2, and A3. Our epsilon matrix is going to be a symmetric 3x3 matrix. Two, 3, 1, 3. Oops, 2, 3. And epsilon 3, 3. So this is called the error matrix, or in Python, it's the covariance matrix. Okay, so epsilon 1, 1 corresponds to L equals L prime equals 1, and that element is the square of the uncertainty in the A1 parameter. So epsilon 1, 1 is sigma 1 squared. It is the square of the uncertainty in A1. right? So what we're saying is sigma 1 squared is sigma A1 squared, which is this A1 in the notation that we've been using for this guy right here. All right, epsilon 2 is sigma 2 squared. So it's the square of the uncertainty in A2, and epsilon 3 is sigma 3 squared, which is the square of the uncertainty in A3. The off diagonal elements, so like epsilon 1, 2, epsilon 1, 3, and so on, those are the covariances of the uncertainty. So typically, if your fit parameters are independent of one another, right? A1 and A2 and A3 are all independent, then those off diagonal elements should be small, and we typically will ignore them. Okay, so the off diagonal terms give the covariances. So sigma 1, 2 equals epsilon 1, 2 equals epsilon 2, 1. Whoops, 2, 1 is the covariance between A1 and A2. We ran into this once before when we were doing the, what we were doing the weighted uncertainty and trying to find the, we're doing the weighted mean, and we were trying to find the uncertainty in the weighted mean, and I think we ran into this there as well. And what we said is if the uncertainties are really random, those covariances should sum to 0. And so that's what we mean when there's no dependence between those two parameters. Okay, good. So what we'll do is we'll just write down a summary of the entire fitting procedure that we developed. And then you will have an assignment 6. I'll probably release it this weekend, where you're just going to implement all of this stuff. And it's lots of fun, so you can look forward to that. So here's the big summary. So fits to functions of the form. All right, y is equal to a1 f1 of x plus a2 f2 of x plus and so on to am fm of x, which is the same thing as the sum of k equals 1 to m of ak fk of x. So we have measured xi versus yi plus or minus sigma I for I equals 1 to n. All right, and we know that A is going to be equal to epsilon times beta. And so the steps that we have to follow to get this A column matrix, our column matrix of best fit parameters, is the following. So this is a column matrix of our best fit values. So the first thing you do is you calculate the elements of the beta column matrix and alpha square matrix. Okay, and we'll write down how you do those calculations. So beta had yi over sigma I squared times FL of xi. All right, and so just L is going to be from 1 to m. And so you end up with m entries in your column matrix. And everything here is known. You know your y values, you know your x values, you know your sigma values, and you know the form of those functions of x. And then the alpha matrix entries. So there's two indices, and it's a sum from I equals 1 to n of 1 over sigma I squared FL of xi k of xi. And once again, you have everything. Once you have your set of measurements, you can just calculate all of these elements. Okay, and so that's step one. Step two is to invert alpha to find the error matrix. So epsilon would be equal to alpha inverse. And, you know, if it was a 2-parameter fit, maybe you do that by hand for inverting a 2x2 matrix. That's pretty straightforward. But if it's bigger than that, if it's 3 or 4 parameters, then you would do this in software. And so you could use whatever you like. So Python or MATLAB or Maple or whatever you like. Okay, so 3 is then you calculate the best fit parameters using A is equal to the error matrix times the beta column matrix. So now you have your list of best fit parameters, and you're going to find the associated uncertainties in each of those just from the diagonal elements of the error matrix. So the diagonal elements of epsilon give the uncertainties in the parameters. And so sigma A1 is going to be the square root of, I mean, I guess the diagonal elements of epsilon give, I don't know, the square of the uncertainties in the parameters. And so sigma A2 is going to be the square root of epsilon 2, and this would just keep going till you get to your last one, sigma AM of your mth parameter is the square root of epsilon MM. Okay, good. And so that is how you would do, you know, we've done our first now fitting method for functions that are nonlinear. It's still not completely general, right? We always had to have, this works only for functions where we have an unknown parameter times some known function of x plus an unknown parameter times some other function of x. What we'll have to do next is we'll have to generalize this to like arbitrary functions that we want to fit to, where maybe we have our parameters mixed in with like some exponential or under a square root of some function of x. And so we'll have to develop a third fitting method. And it's not going to be as pretty as the two that we've done so far. And the reason is that for the two that we've done, linear fits, and now this type of fitting, we calculate exactly what the values of the parameters are and what their uncertainties are. There's no guesswork. The data just tells us precisely what the results are. For the general nonlinear fits that we're going to develop next, we're gonna find that there's a bit of guesswork involved. And so we'll see how that all falls into place, starting on Friday. Okay, good. Thank you very much. And we'll see some of you in the lab right now, and the rest we'll see on Friday. Yeah.